Yep. So this paper is called SILCO. It's called See a Few Images, Localize the Common Object. It was presented at ICCV 2019, and I'm presenting it to you now. This is sort of a table of contents of what we'll be going over. So the first thing is we'll sort of introduce the problem. This is a novel problem. It hasn't been researched before, so we'll make sure to go over that in some detail. There's also some related work on some related problems, which we'll also go over because our authors use some of that existing technology and existing ideas to expand their solution. There's also the method that we'll go over, so their implementation and their results. So first is the problem introduction. We'll just go over the inputs and the outputs of the network. So there are two inputs, or I guess a couple of inputs to the network. The first thing is a support branch. So these are a couple of images, anywhere from 3 to 9, or potentially even more, images that all contain pictures of the same class. And then there's also a query image along with that, which also contains the same class. The goal of the network is to put a bounding box around the common class in the query network. So you can kind of see in the query image. So you can kind of see on the right here, we have, on our support branch, we have 4 pictures of dogs. We have a query image with the dog in it. We want to put a bounding box around the query image with the dog. So the advantages of this kind of approach versus more conventional learning approaches is that it requires a lot less data in order to train it, and in order to actually get good results afterwards on evaluation. Because the support branch not only doesn't require bounding boxes, it also doesn't even require class labels. They all need to be of the same class, but the network itself doesn't actually need to know what that class is. So that's kind of these support images are kind of weakly supervised. And then this network is also potentially very valuable in combination with other networks. So for example, the support branch, in order to get images that are of the same class, we can use an existing classification method and then sort of tack this on the end and get bounding boxes. So that's the existing problem. We'll talk a little bit about related work. So the kind of precursor to this problem is few-shot classification. The idea here is the image on the right that I have here is one-shot classification. So there's one-shot and few-shot classification. The methods are sort of similar. For one-shot classification, we essentially look at 2 images and say, are they the same class or not? And we train a network to figure this out. And the advantage of doing something like this is that we can actually evaluate the network on entirely novel classes it's never seen before. So the idea is that the network learns not just the difference between, not just the similarities inside a particular class, but it learns to differentiate classes. It learns to figure out how to figure out generally if this class is similar to another class, or this class is similar to another image. And this is the foundation for the similarity module of our network, which we'll look at in a bit. The primary way to solve one-shot classification is Siamese networks. And this kind of network is essentially a fully connected network. It's 2 fully connected networks with the weights tied together, so they're the same weights. You run one of the networks on one of the images, and then the other network on the other image, and you sort of compare results. And the idea is that the network can learn to figure out whether the images are similar or not. There are also prototypical networks. These are more common for solving few-shot classification. Rather than one-shot, one-shot. So the idea is that, and also these are restricted to predefined classes, whereas one-shot you can sort of compare novel classes. With this one, you have to train on the class that you want to classify. The idea here is that we generate embeddings for each of the example shots and also for our query shot, and essentially find the Euclidean distance between them in the embeddings. So this actually works really well for few-shot, but again, we're restricted to the classes that we train on. Graph convolutional neural nets are actually great for few-shot classification as well. But we're going to talk much more in detail about those in the method section. So we'll see more detail on those later. Another problem that's closely related to this problem is weakly supervised detection. So that just involves a single image as the input and a single image as the output. The input contains an image with like a label like dog, like we see on the right, and the output is the bounding box around the dog. So that's the general idea. The methods that are proposed for this problem generally require a lot of labels. Particularly to train, we need bounding box labels, and for data, we need images that have been labeled with their class. Also, these methods are not able to extrapolate to new classes. Again, we have to predict only on classes that we've trained. This is just a general overview of a network that does this kind of thing. Essentially, we find a class activation map and a couple bounding box proposals, and then we refine those further until we get final bounding boxes for the class inside the image. And there's more detail on that in this paper I've linked below, which you can see on the presentation once it's posted. Object co-detection is another problem in this space. The difference between this one and previous ones is that we are detecting the exact same object in both images, not just an object of the same class. So you can see in the example on the left, there's a red car, a red Camaro. And then on the image on the right, you are detecting the exact same red Camaro. We're not changing, it's not like also a car, we're detecting the exact same object. And this is kind of similar to what we're doing. Again, it has the predefined class limitation, so only classes that you train on will get predicted. Typically, the way to do this, I won't go into much detail, but typically the way to do this is to use conditional random fields. So those are capable of looking at both images sort of sequentially and figuring out how they relate to each other temporally. Yeah, so how SILCO is different from these previous methods is that they sort of combine the benefits of a lot of them. The whole thing is, so like for one-shot classification, you can only give it one image and it will only give you predictions based on that one image. For other more weakly supervised networks, you need a lot of images, like potentially thousands of images with bounding boxes and with labeled data. So this network sort of circumvents both of those things. It also circumvents the predefined classes of many of the other methods, like co-detection. So instead of having to predict only classes that you've trained on, we can now predict all sorts of different classes that we've never seen before, like bounding boxes for classes we've never seen before. So we'll go over their method. How do they accomplish this? This is the overview that we saw before. You can kind of see that we take all of our support images and our query images. We send them through a backbone first, and then a spatial similarity module, which determines the similar features in all of the images. And then we run it through a feature reweighting module, which determines which of these examples are important. And then finally, we have a detection module at the end, which gives us our final bounding box. And so this is the exact same network in much, much more detail. So we'll go over this bit by bit. So the first couple bits are the backbone networks. These are, well, I guess they're essentially the same network. VGG is used for feature extraction, so the state-of-the-art classification network. We essentially just take VGG features and send them forward to the intermediate modules. So the idea is that we get the support features for each of the input images. So we get support features for the query image, and then each of the support images, how many ever there are. Finally, this other module here is at the end of the network, actually. So we're going to talk about, we're sort of going at, starting at the ends and working towards the middle of the network. So this other end at the end uses, it would normally, essentially like if you put the backbone and this end network together, it's just SSD, which we've seen many times before. This end component detects bounding boxes on sort of multiple scales and gives you a result. So again, we have the backbones, which extract features, and the ending module, which takes features and gets a bounding box. So now we're talking about the part of the network that's in the middle. So the interesting thing about this is that they sort of come up with a baseline that actually gets like reasonably good results compared to their intermediate modules. And that baseline is just using global average pooling. So their suggestion is to sort of average together all of the features of the support images, and then sort of just tack on the features from the query image. And if you sort of just like mash all of them together, you get reasonable results actually. For this problem, you get like a reasonable result, a reasonable bounding box on the query image at the end. But they mostly introduce this to compare their network to this baseline. This is a very simple baseline. And so they show that their like much more complicated structure can achieve better results. So this is actually their first module in the sort of center processing step. This is the spatial similarity module. This is actually, it looks complicated, but it's a little bit of a simple concept. The idea is we take the query image and compare it to each support image individually, one by one. And we attempt to find the similarity between those images. So we take the query image, we find what's similar between it and the first support image, and then again for the second support image, and so on. You can see that they're not actually using a whole lot of complicated convolutions or anything. They're mostly one by one convolutions and matrix multiplications, along with a couple of normalization steps. This structure is kind of inspired by some of the few shot learning methods that were used before, or that I talked about before. And so this, the idea is that this effectively determines which features in the query image are similar to those in the support images. So the second intermediate module is the feature reweighting module. And this module is a bit more complicated, both in purpose and in implementation. So the purpose of this module is essentially to try and regularize the output a little bit. The whole thing that they sort of observed about this problem is that when you have very few examples, you have a large potential to have all kinds of outliers in those images. For example, you can see this is an example of the inputs to the network and then its output. So you can see in the inputs, this image in the center, the most salient feature is the dog. I don't even know if you can actually see that. It's tiny in the back, but there's actually a Jeep in the back there. So clearly these images are trying to teach the network to locate cars, but this center image will only be minimally useful. It can only really get like long range features of this car, and it'll mostly just get features of the dog. So their sort of whole concept behind this module is that some of the images that we get in the support network are not going to be as useful as others. For example, we also have a bus here that may not be as useful for classifying a race car. So the idea is to separate out the images that are very useful and sort of weight lower the images that are just kind of background information that give only like not very important information. And the way they do this is they use a graph convolutional neural net, which we haven't seen very much in this class. So I'll go over a little bit about what it is and sort of why it's so powerful. They are most useful for graph data sets. So like social networks and like potentially if you have like a 3D skeleton or something like that, or apparently they're also, I don't know very much about this, but they're applications in biology with like protein interaction. Anyway, there are a lot of existing data sets that are represented as graphs, and these networks are capable of applying the same concepts of convolution to graph data sets. They're also incredibly useful if we can actually model a more complicated problem as a graph problem. For example, the problem that we're trying to solve here is not inherently a graph problem, but the problem that we're trying to solve is which of these images are more prototypical of the class and which of them are outliers. So it's like kind of a cluster, it's kind of like you can kind of remap it to a clustering problem. And as a result, graph convolutional neural nets actually work extremely well for this. So just a little bit about the details. The idea is that we construct a graph that's in the form of an adjacency matrix. The nodes in the graph represent sort of distinct entities that we're concerned with. In our case, it's images. They can be all sorts of different kinds of things. In a social network, the nodes would be people. And then each node has a feature vector. So in the case of a social network, that would be something simple like what are your interests, like what are your hobbies, what do you do on the weekends, what have you posted on your profile. That would kind of be the information in a feature vector. In our case, the information in a feature vector is the VGG, features that we've extracted. So those are like the features for each that are contained in each node. The edges in the graph are sort of the relationships between the nodes. These can either be randomly initialized to just whatever you want, and the network will figure out how to change them, or they can be initialized to a state that's like tries to approximate the end result. So the idea is that we start with a few target labels. So like we say, okay, this particular node, this particular person, in a social network, say like this particular person belongs to the karate club. And it's like, who else is friends with the people who are in the karate club, right? So we label that particular node, and then the graph convolutional neural net will be able to sort of find an embedding where the people who are sort of closely grouped together and hang out a lot will stay together, and people who are not as closely connected will start to be pushed away. So the idea is that like these graph convolutions sort of reweight the graph as they go, looking at each node and sort of adjusting the weights, either contracting them or expanding them as they go. That's sort of like a high level overview. I have a little video here of sort of what happens. So like there have been 4 labels applied to this graph, but the convolutional or the graph network actually does not know like the colors that we've labeled. The colors are like manually labeled, but we can see that the graph conv network is incredibly good at separating sort of cliques within the group that are like closely related to one another and that share a lot of features with one another. So they're very, very powerful at sort of grouping tasks like that. So the way we use it is we use it to reweight the support images. We try to figure out where is sort of the center of the support images, what images are representative of the class, and which ones sort of aren't really part of the class. And the idea is, so like the 2 steps that we do is we predict the initial adjacency matrix, sort of where we expect them to be. And then as the network trains, it becomes better and better at separating them and finding clusters. So that's a general overview of how the feature reweighting module works. Just to mention briefly, the loss function that they use and how they train. So the loss function that they use two different kinds of loss. The first kind of loss is bounding box regression, which is fairly standard for SSD and like other bounding box detection networks. And then they also use cross entropy classification loss. It's kind of a weird cross entropy loss because they only have one possible class, but they still try to optimize. They still try to convince the network that this bounding box is of the class that is of like our singular class. So we're not like combining a bunch of results and saying, okay, which class is, like normally for classifiers, we'd say, okay, which class is more probable. In this case, we just try to convince the network that the class is in fact in this location. So that's an overview of how the network works. Actually, I should mention here before I go on, we need some of the actual terms here. We need a bounding box in order to train. So in order to train the network, we actually need a single bounding box for the query image, but it's worth noting that we don't need bounding boxes for the support images. We just need to know that they're from the same class. So we can actually train with, that's the reason we can train with a lot less data, is because we only need the one bounding box for the query image. So results. First, let's go over the experimental setup. Since this is a novel problem, there are no data sets for it yet. So they have to modify them. They have to modify the existing detection data sets in order to get this to work. So the way they do this is they take existing detection image data sets and they sort of split them in half class-wise. So like, for example, we'll see in a minute, they use the Pascal data set, the Pascal VOC data set. They use both 2007 and 2012. That data set has 20 classes. So what they do is they split it in half class-wise. They create one group of 10 classes, and they create another group of 10 classes. And the idea is that they train on the first group and then test on the other group. So the interesting thing is that they are testing on classes that the network has never seen during training, which is super interesting. And then they also end up using a video data set just for evaluation. The idea with that is that they train the network on an existing detection data set, and then they essentially like take a bunch of frames from the video or a bunch of frames from different videos for their support images, and then they run and then they pass the query image that they pass in is essentially every frame of a video clip. And so they are able to get bounding boxes for each frame of a video that way. So the actual data sets, just very briefly, I already mentioned Pascal. That has 20 classes. They divide it into 2 globs of 10 classes, train on one, test on the other. Same thing with MS Coco. This time it's 80 classes. So our 2 blobs are of 40 classes. And then I mentioned that the video data set is ImageNet Vid. They only evaluate on it. They train on Pascal, and then they evaluate on basically all of the clips frame by frame. So the first part of the results is the ablation study. I don't have the table here, but it's important to note that they decided to go with local spatial similarity over global spatial similarity. So global spatial similarity would be something along the lines of take all of the support images, sort of take their features and mash them together first, and get what's common between them first, and then compare that to the query image. That's sort of global spatial similarity, and they found that that works significantly worse than local spatial similarity, which is compare the query image to each support image individually and sort of combine the features after the fact. So they find that local is much better. They see significant, you can see over on this table on the right, that they see significant improvements over their global average pooling baseline, which I mentioned earlier. And then also the feature reweighting module improves their results slightly. Sort of the qualitative results, I think, sort of show why this module is so powerful much better. So I have a giant example here for you. So you can see this is the same example as before. You can see that we kind of have the dog image with the Jeep in the background here, which is not super useful. And then we also have a bus image here, while all of these images may be a little bit more useful for classifying a race car. So we see these results on the left here are without the feature reweighting module. The feature reweighting module is just completely gone from the network on the left here. And we can see that instead of getting the car, it just gets the biggest feature in the image. It just gets a large box somewhere. Whereas if we can better focus on the support images that have cars in them, we can actually get a much, much better prediction, a very accurate prediction on the car. And you can see this also in the class activation maps down here. There's also another example with boats. So we could see on the left here, without the feature reweighting module, the network actually doesn't detect any boats in the image at all. Whereas if we can reweight, potentially, because there's a lot of details on the boats here, we want to reweight the images up here that have more boat in them, as it were. So the feature reweighting module is able to do that. And we can see that in the class activation map as well. It's catching much more of the details, and it's giving us good bounding boxes. They also investigate sort of for the whole network, the effect of the number of support images that you give it. Because remember, that can be anywhere from, they test anywhere from 3 to 9, that could be potentially even way more support images. They find a couple of different things. The first is that they reach sort of their peak precision fairly early. So there's kind of diminishing returns as you give it more and more images. So they find that around 5 images, you get most of the detection power of the network. The other thing that they note is that when compared to their baseline, you can actually see that the global average pooling baseline, when you give it more images, it actually starts to perform worse, which is really interesting. It seems like the global average pooling baseline doesn't really, can't really use the extra information to the best of its, it can't really use it properly. Whereas their intermediate modules can absolutely use it properly. their results continue to improve even up to 9 images and potentially further beyond. Also, the gap between the two continues to widen as a result of that. So that's very promising. They also note the effective object size on their accuracy. So they find that the first thing to note is that they perform significantly worse on small objects than they do on large objects. And so that's like sort of one of the limitations that they found with their network. I guess just potentially because the image, they don't get enough information out of only a few images for small network, or for small objects. And this sort of results in much worse performance on the MS COCO dataset. I've included an image from that dataset here. There are actually like a lot of, like, I don't know if you could see that knife down there. There are like a lot of like very tiny objects in this dataset. And the network is expected to sort of detect those and determine where they are. And so that data set is potentially much, much harder to do simply because a lot of the objects are small. So that's the first thing to note, is that small objects perform way worse. The second thing to note is that they are seeing improvements over the baseline on every scale of objects. So they're like sort of, their approach to this is actually capable of collecting information, even on small objects where it struggles. It's capable of actually collecting more information than that baseline. So that's very good. The third thing to note also is that on medium objects, they see the largest increase. So whereas the baseline is fairly good at detecting large images already, is not so great on medium, whereas their feature reweighting and their spatial similarity modules are able to better capture those features on medium images. Couple of success and failure cases. We could see it does great. The couple of images on the left, we actually have a lot of example images with not just a horse in them, but like lots of other people in them. And this query image not only has the horse, but it has a human, which means there's a lot of other features in addition to the horse features, and it's able to locate the horse almost exactly, even in sort of busy support images and busy query images. And that's amazing. We see almost the exact same thing with the cow here, and all of this information in the image is parsed out super effectively, and the cow is narrowed down. We can also see that it's able to detect multiple instances of objects, even if it's only given training on like a single instance. So we see here that it detects the TV monitor, it detects both TV monitors, even though it's only been trained on one. We can also see that there are some examples here that are like less than ideal, they're not amazing, they're okay. And we see that the network performs fine anyway. It's able to learn those features from the better examples and perform excellently. There are a couple of failure cases, however. There are a couple of things that cause them to fail consistently. The first is saliency. Whenever there's a very large image whenever there's a very large object in the query image, often they'll just detect the large object. Often they'll just say, oh, the large object is the, in this example here, they'll just say, oh, the flower is the train, just because it's huge. So that's kind of a common failure case. I already mentioned that object size greatly messes with their accuracy. So like you see this tiny boat here will never be detected just because of its size in the image. They also lack sort of a way to reason about context information. For example, like the network is detecting those two monitors as chairs, even though they're kind of on top of the table. Whereas other more conventional networks might be able to figure out some sort of context information and be able to say, oh, well, that doesn't really make sense. Their network is not able to do that just on a few images. The last failure case is kind of when there's a difficulty. We saw previously that we can get two separate instances of the same object, but they run into issues when it's very difficult to determine the boundary between the two instances. For example, here there are two buses, but they're kind of overlapping in the image. As a result, the network in red predicts kind of like the whole general area as a single bus and is incapable of figuring out that there are two buses and that there's a boundary between them. Their comparative evaluation is also the results are also fantastic, but they compare against, since there are not really any other networks in this area yet. They're comparing against baselines that are not ideal. The center box baseline that you see at the top is essentially, we've just put a center box and say, oh yeah, that's where the object is. And as you can see, it performs pretty badly. What they take from this is that just that the problem is very hard, that by randomly guessing where the box is, you're not going to get a very good accuracy. So that's sort of validation that what they've done has made significant progress and on a very hard problem. The RPN and contrastive RPN networks are sort of more conventional neural nets that they train on just a couple of images. So of course they do not very well. Even the interesting thing is, even with contrastive RPN, they include a Siamese network, which I mentioned before are good on view shot learning, and it still doesn't perform nearly as well as their methods. So it's really interesting to see that they have been able to extract this information so well. So to sort of summarize and conclude, the problem that was presented in this paper is novel. It's called few shot common localization. That is, look at a few examples of an object class and detect that class in the final image. It's an incredibly useful, problem and network that they've presented, because it allows us to sort of get cheap bounding boxes. Whereas previously we would require thousands and thousands of images with labeled bounding boxes, we may require significantly less images with bounding boxes in order to train this, since we can use a lot of unlabeled data for the support images. The way they achieve this is using a spatial similarity module and a feature reweighting module, which are kind of inserted in the middle of SSD. The spatial similarity module is capable of finding the similarity between images, so it's able to detect the common class. And then the feature reweighting module is able to determine if we have an outlier in the support images, and is able to sort of reweight that and focus more on the better examples. And of course, their network beats the existing baselines by a large margin, and they sort of open up the problem to other solutions from here. So yeah, that's all I have.